Hello and welcome back everybody. Today in calculus we will discuss how to solve for length of a curve. So in short, how to solve for what is known as an arc length. So on the right hand side you can see that we have a picture of a function. We can go ahead and call this f of x, and what I would like to do is not solve for the area underneath the curve from a to b, but rather what is the length of the curve from a to b then. So meaning where this black dot right here begins. So this is going to be my start, and then we're going to figure out what is the length going all the way to the end according to the curve. Now, in order to do that, just like everything else in calculus so far in the second semester, we're going to have to look at a small little section and then try to dissect what's actually happening. But before that, what I'm going to do is I'm going to consider the following then. If you remember, like when you were younger, maybe you played with this one toy where you have a snake, where you can kind of like, I guess kind of like flip it around or fling it around. But the snake itself consists of a whole bunch of rectangular parts that looks kind of like this. So, then that right there kind of like makes up the snake, even though, it's not like completely curvy. So over here, that's exactly what I want to do. I want to take that curve and I want to make it so that it looks like a whole bunch of these little rectangles, or actually not these rectangles, but more of these little line segments. If I look at a segment small enough, then we can definitely do that. So why don't we go ahead and do so then, okay? So here, you'll notice that I've isolated a small little portion, which is going to be that little blue box right there. Now, if we magnify that blue box enough, then this is what it's going to look like inside. The inside part of it is going to almost look like a curve then. So here, let me just go ahead and draw that over here, okay? So if you can kind of imagine it, when your window is small enough, that curve is almost like a tangent line. And in fact, it's pretty much just like a tangent line according to my first semester of calculus. Well, here, what I will do is, since it's going to be kind of like a tangent line at that small little localization area, what I can do is draw a right triangle in this case, okay? So in this situation, we're going to go ahead and draw kind of like a small little piece right here. So that is going to be a small piece of the arc length right here, which we're going to go ahead and denote as S, okay? Or actually, we're going to denote that as delta X, S. I think that actually sounds a little bit better. Now, that delta S is going to be, you can solve for it because it's a right triangle by the following. The horizontal component, we're going to go ahead and call that the change in x, whereas the vertical component, we're going to go ahead and call that the change in y. And so if we put it all together, then that means that delta s, that small little piece of arc length, is equal to the square root of delta x quantity squared plus delta y quantity squared. So this right here is a small piece of the arc length, okay? So small piece of arc length. And what I want to do is find the sum of every single one of those arc length. So then that means that the total arc length, which we'll go ahead and denote as S, where S is going to be the entire length from here to here, is going to be the summation of every single one of those small little pieces put together. So we'll take the previous equation and we'll put a summation in front. And normally we would say, okay, well, this is where the integral comes in because we have a summation, we have a delta, but we have a delta x and also a delta y. So that means that this is going to be problematic. So we'll go ahead and take a small little, modification to all of this. And here's what we'll do. Let's say for the inside, I'm going to go ahead and factor out a delta x quantity squared, okay? So for the inside right here, I'm going to go ahead and factor out a delta x quantity squared. So factor delta x quantity squared. If I do so, the first part will definitely just become 1. And then the second part right here, well, before I write the second part, let me just write that delta x quantity squared factored out. If I'm factoring out, that's going to give me delta y divided by delta x quantity squared. And that right there tells me now my equation, because if you look carefully enough, the delta x quantity squared, that is going to go outside of the equation. And for the inside equation, you might or might not recognize this, but delta y over delta x, that's really just saying the derivative. So in the end, what you're going to get is the following. If my equation is f of x, then the arc length from a to b is going to be the integral from a to b dx and time, and then you have the square root of 1 plus f prime of x quantity squared. So that is going to be what I'm using as my formula then. Okay. All right, so let's go ahead and try this on a few problems just to see how this actually works out then. So for this first problem, we say determine the length of y is equal to 1/3 times 4 minus x raised to the power of 3/2 between 0 to 4 for x. And I drew, well, I didn't draw it, but Desmo drew it for me. The picture is on the right-hand side. Now, for the most part, you don't really need the picture, but it's just nice to kind of have just to see like what is it that I'm trying to solve for. So essentially in this problem, I'm trying to solve for this length right here, this little curve length. So going by my guideline, what I need to do first is I need to solve for the equation of the derivative in order to plug into that arc length equation. So first, we'll go ahead and say that y is equal to 1/3 multiplied by 4 minus x raised to the 3/2. So y prime is going to be equal to 1/3 multiplied by 3/2 multiplied by 4 minus x raised to the power of 1/2. The 3's would cancel out, leaving you with 1/2 times that. So I like this nice and clean equation. And what we'll do next is we'll go ahead and throw it into the arc length equation. S is equal to the integral from, in this case, it's 0 to 4, and then times the square root of, or not times 2, but the integral of the square root of 1 plus y prime squared. Now, y prime squared, that's what's above. So that's going to be 1/2. Times 4 minus x raised to the 1/2, and then the whole thing squared, and then dx. So if we can solve for this antiderivative, then we are pretty much home free then. So we'll go ahead and clean up that equation. The square root of, for the inside, you have 1 plus, looks like we have the 1/2 and the square cancels out, so that comes out nice and clean. We do have that 1/4 because it's 1/2 squared, and then multiplied by 4 minus x dx. Okay. Keep trimming it just to see what we get. From 0 to 4, I'm going to go ahead and write the square root of, looks like it's going to be 5 plus, oh, actually, you know what? I don't want to skip any steps. Let's go ahead and write out the whole thing just in case, okay? We're going to get a common denominator of 4 over 4 plus 1 over 4, and then 4 minus x, and then we have dx. Let's see, we're going to take out the 1/4, so that means we're really taking out a 1/2 because it's inside the square root. And then when the inside, what we have left is 4 plus, looks like it's going to be 4 minus x. Okay, just checking, make sure everything's okay. Taking out the 4 on the bottom, and then on top we have 4 plus 4 minus x. Yes, that looks okay. So now just to clean it up a little bit more, so 1/2 square root of 8 minus x dx. We can solve for this problem using a u substitution. Let u equal to 8 minus x. So du would then be equal to negative dx then. So if we go ahead and continue on over here on the right hand side, my boundary, since this u is equal to 8 minus x, my lower bound is now 8 minus 0, which is equal to 8. And then my upper bound is going to be 8 minus 4, which is equal to 4. And then we also have the 1/2, and then we have the square root of u, and then we have negative du because we have to replace everything back in terms of u. That works out nicely because the negative and the 8 and the 4 can cancel out. So now we're going to flip it back from 4 to 8. We're going to go ahead and put the 1/2 outside, and then we have the square root of u du. Antiderivative of square root of u is going to be u raised to the power of 3/2. Then we have 2/3 multiplied by the 1/2 on the outside, boundary from 4 to 8. So the 1/2s cancel out, giving you 1/3. Plugging in the 8 into the equation, then we are going to get 8 raised to the power of 3/2 minus 4 raised to the power of 3/2. And each one of those, they can't be simplified if I'm correct. Oh, wait, ooh, I think I skipped a whole bunch. Okay, so good thing we didn't lose that. So let's see, 1/3, this part right here, we can write it as, well, I guess, I don't think it's going to come out nice. So I think we'll just go ahead and leave it as 8 raised to the power of 3/2. And then minus, for this guy, we can write that as 2 to the 3rd. So this part right here, let me just write it out. 2 squared raised to the power of 3/2. The 2's cancel out, so we have 2 to the 3rd, which is going to be 8 then. Okay. So yeah, right there, that is going to be our answer then for the arc length. All right, so now let's go ahead and look at another problem, similar, almost identical in a way, but there's going to be a small little change right here, okay? So determine the length of the, I guess, curve for the equation y cubed is equal to x squared between 1, comma 1 and 8, comma 4. Now, what makes this a little bit more difficult is that it's not just y is equal to. It's going to be some sort of, I guess, a relation in a way because it's y cubed is equal to x squared. Again, the curve is over there on the right-hand side, so you can kind of see how that actually looks like. So let's go ahead and, go by our, what we've been doing so far just to see how it goes. Now, if I make the, I guess if I make the substitution, then we're going to go ahead and first solve for y, which is going to be equal to x raised to the power of 2/3. And if I take its derivative, then that's going to give me 2/3 x to the power of negative 1/3. Throwing it into my equation, we're going to get the integral from 0 to, not 0. The integral is going to be from 1 to 8 because if you notice, it's from the 0.11 to 8.4. So that's where I got that from. And then we have the square root of 1 plus, in parentheses, 2/3 times x to the power of, let me go ahead and clean this part up a little bit more. 2/3 times x to the power of negative 1/3 and then squared and then dx. Now, needless to say, this is not exactly something nice, but we do have an integral to actually work with. So, if you're looking for just an integral answer or something you can throw into your calculator using finite integration, we're pretty much all set. So here, let me just kind of clean that last part up, which is what you have right now. So 1 plus, looks like it's going to be 4/9, and then x raised to the power of negative 2/3 dx. So that would be my, I guess, representation in this case. Now, it's not to say that we can't actually solve for this because if you look at our equation right here, we're not restricted to solving for y like we normally would. We can also solve for x, and that something is, that basically means that we're going to have to change our equation a little bit. Here, let me refer you back to my original equation, which is this guy over here. Now, in the second step, if you remember, we factored out the delta x squared. But what happens if I factor out delta y quantity squared instead? If I do so, then that's going to change my equation as the following. The summation of the integral of 1 plus delta x over delta y quantity squared delta y. And what that means is now we can have a same thing, we can solve for the same thing, but using dy instead of the square root of 1 plus dx over dy quantity squared. So it's this equation is actually pretty versatile. You can use dx or you can actually use dy. But then you have to keep in mind that means that you have to look at the vertical boundaries. So that means it's going to be from f of a to f of b in this case. So here we have f of a all the way to f of b. Now, in terms of how does that work out in our problem over here? Well, what that means is we're going to go ahead and solve for x instead and then take the derivative. So let me go ahead and kind of put this on the side. Okay, it's not wrong, but again, I would like to solve for this if possible. So x, according to our equation, right, is going to be equal to y raised to the power of 3 over 2. Okay, and then now if I solve for dx dy, then that's going to give me 3/2 times x, not x, used to writing x every single time, but it's not that case. 3/2 times y raised to the power of 1/2. Okay, and that's nice because now if you notice, when I plug it into that equation, I can actually go ahead and get something nice and clean. So the integral in this case for the using dy is going to be, now be very careful once again, it's going to be 1 all the way to 4 because those are the y values. And then we have the square root of 1 plus the derivative with respect to y. So that's going to be 3/2 y raised to the power of 1/2, the whole thing quantity squared. And if we just cleaned it up a little bit more, then we have 1 plus 9 over 4y and then dy, which definitely is a lot easier to solve for because you can use a u substitution. Okay? Okay, And finally, for this last one right here, this is just going to be a set up an integral to represent the length of the curve y is equal to x times e to the negative x from x is equal to 1/2 to x is equal to t. So what that means is my endpoint is just going to be anywhere. Okay, it could be like at 1, it could be at 4, it could be at 5. It's just going to be some variable that's representing the endpoint. Okay, so let's go ahead and go through our procedure so you can see what that looks like. First, we're going to go ahead and solve for y prime. Y prime, according to the product rule, is going to be the second equation multiplied by the derivative of the first, plus the first equation multiplied by the derivative of the second. And if we clean that up, that's e to the negative x, and then multiply by 1 minus x. So now, if I'm going to put it into my arc length equation, then then it's going to be s, which is the arc length, is equal to your starting point is going to be 1/2 all the way to your endpoint, which is going to be t. And then we have the square root of 1 plus e to the negative x, and then 1 minus x, the quantity squared, and then we have tx. And so right there, that is going to be my representation of the curve then. And if you notice, it looks very similar to that of FTC1. So, now you get an idea of how to go back and, try to figure out what you can possibly do with this thing, okay? All right, well, thank you so much for watching. I will see you guys next time. Have a good one. Goodbye.